Welcome to the third video in the probability section. This video is about the use of Venn diagrams. There's some quite tricky little problems in this particular area. My view is Venn diagrams is a rather strange way of representing probabilities, and I think if you're sometimes a bit confused by these problems, it's not your fault. It's because the problem setters are actually trying to set problems on a tool which has a dubious value in my view, but nevertheless it's what's done, and we need to be able to rise to the challenge. So let's hopefully can actually deconfuse it a little bit for you. Okay, so Venn diagrams, yeah. Well, we're assuming here that you've got a little bit of knowledge of set theory, but not too much knowledge. But just what we mean by Venn diagrams, and really what we're doing is we're describing the space, for a set of events. So typically, if we have two events here, A and B, these overlap, so A and B can both happen, because we've actually got some content in there. It's not zero. When we're doing these Venn diagrams, we tend to either put probabilities in them, or we put actual values, numbers of things. And as a result, if they're numbers, then they're effectively probabilities, because here in this diagram on the left here, we've got 3, 1, 3, add 1, add 4, add 2, that's 10 altogether. So the probability of A happening is going to be, it's got a total of 3 and 1, 4 out of 10, 4 tenths. So the probability of this total of A would be 4 tenths, 0.4. So now we're not saying what A and B is here. We'll come on to some examples, which will make it a bit clearer. But that's what we're doing on here. But I say equally, we could actually represent all these by probabilities with 0.3 and so on. Okay, so if we just look down here, these are the sort of things that we see in our probability problems, very often with Venn diagrams. Probability of A, we've just sort of said, well, it's 3 and 1 out of the total of 10. So always remember this bit here. This is the bit kind of outside the circles. Means it's it's a sort of the void space or whatever we want to call it. So that's 4 tenths. Probability of B is 1 plus 4 out of 10 is 5 tenths. Probability of A intersection B, that's the probability of both A and B happening. We will have an event which satisfies both A and B. Well, that's this space in the middle here. That's the intersection. That's just 1, so that's 1 tenth. A union B. Union B is what happens when we put all these spaces together. 3 add 1 add 4, that's 8 tenths. And this little dash here, A prime, means not A. When we look at the occurrences or the probabilities outside of A, we've got the 4 and the 2. So the probability of not A would be 6 tenths. And then we get more complicated things. The probability of A prime intersection B. Well, A prime, we just said, is these two. B is these two. So the intersection of those two and these two would be 4. So that would be 4 tenths. So the things that we are interested in our Venn diagram would be the independence of events. Now, we're going back to our probability trees. We noted that we could multiply horizontally across the trees. And what we're doing is we're multiplying two independent events to give us the intersection of those two. Now we can look at this the other way around and say, well, if the product of the two is equal to the intersection of the two, we might be given these separately. Then if they are, then they're independent. So we're kind of working around sort of saying, we're assuming these are independent, therefore we can multiply them. What we're saying is if we can multiply them and get the joint result, then they are independent. So it's just kind of reversing the thought process. So that is that particular rule, crops up all the time. Mutually exclusive. So can different things happen? Now, in our probability tree, these A's and the B's would be rows or leaves in the probability tree. Can they both happen? Well, if they can't both happen, probability is 0 of them both happening. Therefore, their intersection it would be 0. So that would be the test for whether or not they are mutually exclusive. Now, this really does kind of start to run a bit obliquely to the idea of the probability tree, because we have a different perspective on what we're talking about, independence and mutually exclusive. Here, it's all brought into one diagram, which takes a little bit of getting your brain around, I think, myself. Okay, the other rule that comes up and we need to use is this one, the idea of the probability of the union. Just going back to this one here. Notice if we could get this by if we add the probability of A, which should be 4/10, and the probability of B, which should be 5/10, we would have double counted this middle bit here, the intersection. So so we would need to subtract that from the sum of these two in order to get the probability of the union, and that's exactly what this equation does here. Probability of the A union B is equal to probability of A plus the probability of B minus the probability of the intersection. So we're just kind of taking out one instance of that thing that would otherwise be double counted. Okay. Now, also in Venn diagram speak, we often get into all this complicated stuff, and we have to evaluate these sort of things. Now, you could remember, try and remember all these formulas. Personally, I think it's not necessary. It just leads to mistakes, I think, and confusion. We'll come to this, and basically, if you need to work these sort of things out, the best idea is to kind of sort of, just kind of work through it methodically, starting from the sort of the inside, by which that meaning will become clear in a short while, and work it out. But actually trying to remember these things, if you've been presented with these things and you think you need to remember them, then you don't. Okay, so that is a bit of an overview of Venn diagrams. Let's go on and have a look at an example. Here we go. The Venn diagram in figure 1 shows the number of students in a class who read any of 3 popular magazines, A, B, and C. Okay, so this is numbers. So what we're sort of saying with this is, if we pick any student at random, then what's the probability of them reading all 3 or whatever it happens to be? So we note if we add all these up, we get to 30, total 30. So in this case, the probability of them reading A would be 4 plus 2, that would be 6/30, 1/5. Okay, so let's have a look at the actual questions then. One of these students is selected at random. Show that the probability that the student reads more than one magazine is 1/6. Okay, well, just by looking at this, we can see, well, we've got something representing A and B and something representing B and C. So the probability but these two spaces themselves don't actually intersect. So therefore, we can just add these two together. So the probability that they read or the probability that they read more than one magazine is the probability that they read A and B plus the probability they run B and C. And there is no probability of A and C. They're not intersecting. And there certainly is no intersection of all three, A, B, and C. So we can just write it like this: the probability of A intersection B plus the probability of B intersection C. And that would be 2/30ths at 3/30ths, which would be 1/6. Okay, so that's part A. Find the probability that the student reads A or B or both. Right, well, that's what this is saying, A or B or both. Yep. So just going back to our example a bit higher up, that is the union, probability of A or B or both. And that would be, well, what we got, it's all everything in this space here. Yeah, 4 plus 2 plus 5 plus 3 out of 30, 14/30ths, 7/15ths in other words. C, write down the probability that the student reads both A and C. A and C. Okay, well, we've just said there's no intersection shown here. Sometimes there is shown as an intersection, but it's got 0 in it, which is effectively that there isn't an intersection. And in this case, the circles aren't even drawn overlapping, so we don't need to put 0 anywhere. Nobody reads A and C. So that's the probability of A and C is therefore 0. And determine whether or not reading magazine B and reading magazine C are statistically independent. Okay, so now we go back to the test that we mentioned before. Probability of B. This is the probability of C. So the probability of B and C together would be this intersection here. That's 3/30ths rather, which is 1/10. The probability of B is this circle here. Well, we can see that's 2, 5, 3. That's 7 out of 30. Sorry, that's 10 out of 30. 2, 3, 5 is 10. Okay, 10/30ths. And the probability of C is these two, which is 3 and 6. That's 9/30ths. So probability of B times probability of C is 10/30ths times 9/30ths, which equals to 1/10. And that equals this value that we just worked out. So therefore, we can say that the probability of B times the probability of C equals the probability of B intersection C, and therefore the events are independent. So that is a fairly typical sort of probability problem. Okay, so let's just have a look at that. Another one here. Right, in this one, slightly different. We're actually given we're given probabilities here. We're given these facts. The probability of A intersection B complement is 0.32. Okay. Right, so we've got A and B, and we're showing an intersection here. We might be about to work out that it's 0. We don't know yet. It's possible. But so what we're saying is the probability of A, that's what's in effectively these two bits here, intersection with B complement. And what's B complement? Well, it's the bit outside here, this kind of void here, with this is outside B. So it's the intersection of those two. Well, this bit is the intersection of those two bits. And it's saying that is 0.32. So we can fill that in there, 0.32. The probability of A prime intersection B. This question's actually kind of written it wrong. I've written it correctly above. Probability of A prime intersection B is 0.11. Well, this is rather similar to this, but it's the other way around. In actual fact, it's this space here, 0.11. And then the probability of A union B is 0.65. So that's saying this and this and this is 0.65. Therefore, since we know this and we know this, then this must be 0.22. Okay, so we're just using a bit of deduction really on this to go through and work out the numbers. Now, and having known that, now we know everything within this box adds up to 1. So therefore, this must be 0.35 here. Okay, so we've got our Venn diagram to illustrate the complete sample space for the events A and B. We've done that. All right, we more or less just go read off the other answers off it, I think. Write down the value of probability of A and the value of probability of B. Okay, well, A is, well, these two, that's 0.54. Probability of B is these two, which is 0.33. So that's easy enough. Find the probability of A given B prime. Now, given B prime means that we're effectively sort of narrowing down our sample space. So what we're saying is, what's the probability of it being in A given that it's not in B? Given that it's not in B. What's the probability of it being in A given that it's not in B? Right, okay, so if it's not in B, it's either this or this. So our total space is actually 0.67. So the probability of it being A is 0.32 out of 0.67. 0.32 out of 0.67. So that is 0.32 divided by 0.67. It's a fraction, really. And that works out as approximately 0.48, well, to 2 decimal places. So that's an interesting kind of point there. Okay, so this is our narrowed down. This is like our new 1. We've drawn it down from 1 into 0.67. So the probability of it being in there is only out of 0.67. So 0.32 is about half, isn't it? Really? Yeah, that's about half of the space left. You know, half of a 0.67 space. So if we can look at it like that, it might help. And finally, determine whether or not A and B are independent. Right, we've all, well, what have we done? Probability of A times probability of B. Well, we've calculated those above. That comes to 0.33 times 0.54, which is 0.1782. The probability of the intersection of A and B is this bit here, 0.22. Well, it's clearly not the same as 0.1782. So therefore, these two events are not independent. It's a bit obscure, really, because we don't know what A and B are. It might be if they were assigned real life things, then it might be helpful. But for the purpose of this problem, it doesn't matter. We can still do the working out and get the answer. Okay, so and finally, I'm going to do that one. The other one, but finally, let's just have a look at this one. Now, this actually quite a tricky problem. I've condensed the answer down into a few lines, but actually, it's not that easy, really. 3 events, A, B, and C, and their associated probabilities. So our 3 circles, and they're overlapping, and we've got the sort of the overlap of all 3 here as well. A bit wavy, this line, but that's just the way I managed to grab it from somewhere else. B and C are mutually exclusive. A and C are independent. Now, as I mentioned before, it starts to get a bit difficult when you compare it to your probability trees. You think, well, they're completely different concepts. But anyway, they managed to put it onto the same diagram. So, showing your working, find the values of X, Y, and Z. Okay, so we are told that B and C are mutually exclusive. That's B and that's C are mutually exclusive. We know that's 0, but actually this whole space, so the intersection of B and C, must be 0. So therefore X must be 0 as well, because we've already got 0 in that bit, but we need to have 0 here as well. So X is equal to 0. So that's that. Going to our second fact here, the probability of A intersection C is equal to probability of A times probability of C. That's because we're told that these two are independent. And so that's the independence condition. So what have we got there for them? Well, the probability of A intersection C is this space here, Z and 0. Well, I've just shown these at Z and 0 because that kind of just helps. Is equal to, probability of A is going to be this 0.10 plus the sum of these. Well, I've left the 0 out there, so plus Y plus Z there. Yeah. And then the probability of C is 0.39 plus Z plus, well, X, but we know that X is 0, so we might as well have that as 0. So that's just Z then. So 0.39 plus Z, so that's probability of C. Okay. So therefore the probability of Z is equal to 0.25. Oh, hang on a minute, what's happened here? 0.1 and Y plus Z. Right, okay, so this is the trick on this one, really. What we've got to do is we're looking at Y plus Z together. We know everything else on this chart, now that we know X as well, 0. So we know that Y plus Z is what's left over after we've, out of 1, when we've taken away all these things. So, so all these other things added up together, that's this lot here, is going to give us 0.15. So we know Y plus Z equals 0.15. Okay, so that, as I say, is the trick on this one, really. So Z equals 0.25 and 0.39 plus Z, that's the probability of C. Well, if we just work that out, we multiply that through, we group our Z's together and divide through, then we get Z equals 0.13. And since they add up to 0.15, we know that Y is equal to 0.02. So therefore, we've got our X 0, our Y 0.02, and our Z, which is 0.13. So yeah, I've not got many lines on here, but there's one or two kind of subtle little bits of thinking. But the main thing we've done really is apply these two events. Now this sort of problem where we have to, we don't know all the components, so we have to use algebraic values and use these facts here in order to actually deduce or calculate those algebraic values that we've assigned. Again, that's a sort of fairly typical kind of thing, but they do tend to be a little bit more tricky, these things. But really, if you go about it sort of methodically, then they work through okay. Okay, so that is Venn diagrams. So hopefully I've helped to clarify that. So they are, or at least they can be sort of quite tricky little problems, these, but hopefully that will help. Okay, good. So I will therefore see you in the next video.